All right, so convolutional neural networks, and these are revolutionizing medical imaging. Now, convolutional layers they're designed specifically for image data, and they are revolutionizing medical imaging in ways that most healthcare professionals are only beginning to understand. And we are going to unwrap this today in this video. Now, the simple definition for this would be CNNs are AI systems that examine medical images layer by layer, starting with basic shapes and gradually building up to more complex shapes and resulting in a medical diagnosis. In a way, similar to somewhat when we were in medical school and then in residency, how to read chest x-rays. First thing you do is look at the penetration. Is it underexposed? Is it overexposed? Look at the rotation. Are the clavicles centered? Look at the position of the body. Is the patient the upright, supine? You look at all of these things. Then you look at the airway structures, the trachea, the carina, the hilar region. Then you look at the lungs, the lung fields, the lung markings. So you go step by step. Then you look at the cardiac silhouette, the cardiac size. You look at the diaphragm. Then you look at everything else: bone, soft tissue, tubes and lines, any foreign bodies. So you follow a stepwise pattern. Similarly, although it's not following the exact pattern as humans, however, we will learn right now that it follows a pattern, and that is going to be very important. Now, this is a basic architecture of a convoluted neural network, and this is what we will talk about today in this video. Now, okay, so this, of course, is a chest X-ray. For those in healthcare, they would know this, very easily. Now what happens? So the network takes the original X-ray image and passes it through a multiple steps of specialized layers. You can see this is the convolutional layer, two convolutional layers being shown here. This is just an example. And you have pooling layers, and we'll talk about pooling in detail in a different video. However, just to get you acclimatized over here. So the convolutional layers, they detect medical features such as edges, textures, and patterns in any lung tissue. Then the pooling layers right over here, they reduce the image size. You can see here, they are actually reducing the image size, but they look to preserve diagnostic information that is contained. Now you can see, I'm going to talk about these boxes over here. But just keep in mind that pooling layers, they look to reduce the image size while preserving important diagnostic information. This happens multiple times, with each layer learning increasingly complex medical patterns. Now, if you have fewer layers, then you will have less complex detections. If you have multiple layers, many layers, you will be able to pick out more complex medical patterns. And finally, at the end is something called the fully connected layer. Now, the fully connected layer combines all the detected features to make the final diagnostic decision, such as identifying, let's say, pneumonia, nodules, anything else. So this is the basic mechanism by which it works. Now, then there's something called filters, also known as kernels. And in a neural network, these are like small magnifying glasses that actually slide across the image, and they look to find specific patterns or features. Now, they can be bigger and smaller, and they also affect your model training and the output. And like we discuss, every single thing has a purpose. Every single thing is related to some aspect that you will need to understand when you are practicing or assessing vendors bringing in their models. And at the very core, filters in a CNN is a small matrix used to detect specific features such as edges, textures, and patterns. And these filters are applied to this input data throughout this process. And the takeaway message right now is that it is the architecture of the CNN basically how many layers, what size filters, and how the layers are connected, it determines what kinds of patterns the model can detect. A CNN with small filters might excel at detecting some fine details, but miss larger structural abnormalities. A CNN with larger filters might identify broad patterns but miss subtle early stage pathology. So, this will let you know, okay, a model with larger filters, okay, they may be able to pick up cardiomegaly or a big heart a lot better than a model trained on smaller filters who might be able to pick up more interstitial lung disease or small nodules. So, this is an aspect that is important to understand. And that is why understanding a CNN architecture is actually highly important for radiologists and any other imaging specialists. And you need to know what your AI tools are optimized to detect and what they might miss. So you need to understand the trade-offs inherent uh, built in with all the different types of architectural choices. Hopefully this gives you some insight into how you will be the human in the loop in the future, at least with this. Dear all, I hope you are doing great and that you are liking these lessons and you are enjoying and you are learning. And I did want to suggest something as an option for you. Only if and only if you are one of those who want to have this content in a more organized manner, there is a program that I have set up that you can find in the description. It absolutely is not necessary. However, it is only for those who do thrive in an organized approach, and there just might be a few more goodies there as well. Anyways, I wanted to share this, and now back to the video. Think of this like a radiologist's thought process. First, noticing, let's say, edges, shapes, anatomical structures, and then coming to a conclusion regarding the diagnosis that the person will be arriving at. And for medical imaging, CNNs might detect subtle lung opacities on an X-ray before the human eye actually notices this. And this isn't actually science fiction. It's happening right now in hospitals around the world. And CNNs have been actually shown to outperform human radiologists in specific tasks like detecting diabetic retinopathy for the eye from eye photographs, and even identifying skin cancer in dermoscopic images. All right, so we talked about different layers, right? So if we go back to our main diagram over here, so we had different layers as you see over here. And each layer has a specific function in a way. Now let's get over here. So let's say, for example, one layer would be the edge detector, identifies outlines of organs, spots the edges of bones, finds borders between different tissues. Then the second layer, for example, would be a shape recognizer. It recognizes circular shapes such as tumors, identifies linear structures such as bones, blood vessels. Um, so the thing to keep in mind is it necessarily does not need to mimic how a human sees, but you can see, you could be just looking to program, let's say, the prostate. So you as the medical professional will need to know what is in the prostate and what you need to train the CNN for the prostatic structure. Okay, you know the prostate has a capsule, the prostate has its parenchyma, the prostate has two regions inside. So you will design the CNN based on your understanding of the prostate. Similarly, any CNN looking at the brain, looking at the eye, looking at the lungs will be slightly different from any other CNN. Then another layer will be the anatomy expert, recognizes bigger organs, identifies normal versus abnormal sizes, and then you have the diagnostic specialist at the very end, combines all the previous observations and compares to patterns of known diseases and provides diagnostic recommendations. And there have been numerous success stories already. Skin cancer detection, we talked about that. Diabetic retinopathy. Hey, get the image. Anybody can get the image done at a primary clinician's office and just put the image into the AI, and hey, you have the diagnosis right there. Does the patient need further treatment? Diabetic disease is controlled. Has any macular degeneration happening? So yeah, this is now democratizing patient care. As we discussed and demonstrated, chest X-ray analysis. But why are they revolutionary in healthcare? Well, consistency. They are trained and they will do the job. They never get tired or distracted. Apply the same careful analysis to every image. They don't have bad days that could affect their performance. And we all know we all have bad days. Speed. They can analyze images in seconds rather than minutes. Even though, trained radiologists can do it pretty quickly as well. However, not everyone is fully trained as a experienced radiologist. And more importantly, provide immediate results for urgent cases. You are in a remote area, perhaps, or even in a tertiary care center. Tertiary care centers can be very busy. One doctor may think is important for their patient. Somebody else or a radiologist might not think that that case is as important as whatever other cases he or she is dealing with. This will hasten up a lot of image reads and detections. They can spot subtle patterns human eyes may miss because they're learning from millions of images. And if possible, and this could be somewhat of a limitation, but if they're trained properly, rare conditions can also be picked up, especially if if the model has been trained on vast databases. But just the limitations, understanding CNN limitations, what they can do. Well, they cannot replace clinical judgment currently, and of course, they cannot replace patient interaction. Understanding patient symptoms that aren't visible in images. So the intuition that comes with an experienced human. And right now, there are tools being developed. However, it's difficult for them right now, in most situations, to consider patient history and other medical factors. Although this is definitely being worked on. And again, the most important point would be that actually making treatment decisions that require human empathy. So, of course, human in the loop always will be a part of the picture. So, when CNNs might struggle, when the images are itself, they're poor, they're blurry, poorly lit, wrong angle, it could confuse a neural network. Underexposed, overexposed images that could lead to trouble. Some rare conditions, as I mentioned for the last slide, may not be well represented in the training data. So you have to pick out all the diseases so they can be picked up, right? And then they have problems when an image shows multiple overlapping conditions. They have lung disease, they have interstitial lung disease, they have fibrosis, they have COPD, they have bronchiectasis. Simultaneously, they have cardiac problems. You could also have pulmonary edema on top of all of this. And yes, we see patients who don't match any textbook. Images will have a tough time, or AI will have a tough time clarifying that. I mean, yeah, they'll get you some differential diagnoses. However, all of this has to be assessed in conjunction by looking at the patient. See your patient. That's the number one. Go talk to the patient. See the patient. Look at the patient's history. So all of these things matter. Then patients whose anatomy is unusual or is surgically altered. Now, they could have had multiple surgeries. They could have hiatal hernias. They could have had dextrocardia. The heart is flipped. So yeah, a lot of things could be there that could confuse the AI. So that's why humans just don't fully rely on this. Read the report, or look at the image quickly. Yeah. Confirmed. Okay, good. Then let me sum up CNNs, what it means for your healthcare. So let's say from the patient perspective, and patients will be asking this and they will be informed about this in the future. As a patient, they may be knowing that that their medical images might be analyzed by AI before or alongside human radiologists. And they may know that this can lead to faster diagnosis and treatment. AI might catch things that could be missed by human eyes alone. You still need human doctors to interpret results in the context of your overall health. But the questions that they will be asking, and patients will be educated on this in the future. So, was AI used to analyze my images? Right? What did the AI find? Do you agree with this assessment? Are there any limitations to what AI can see in my case? So, in the future, for example, we know, let's say, for example, what is a stress test able to diagnose, or what is it supposed to do, right? We know what is an echocardiogram for the heart able to do, and what is its utility. And a doctor can, of course, tell how useful is an EKG machine for certain conditions, right? So every test has its degree of importance, and its benefits and its limitations. So down the line, we will need to know what are the strengths of this model. And patients may ask us, do we know about this? And how does that relate to my particular situation? And then follow up, do you recommend any additional imaging or tests based on the AI results? Now, having said this, let's go over a little bit on the future of medical imaging and AI. So the accuracy is improving. CNNs are getting better in detecting subtle abnormalities, and new techniques help them explain reasoning, and that's all being developed. And as we talked about previously, there's going to be integration with other medical data, and it improves overall accuracy. Then, what I'm really excited about is expanding applications, real time analysis during surgery, monitoring treatment progress over time, predicting how diseases will progress, and personalizing treatment based on image analysis. All right, so this will, of course, make healthcare more accessible, bringing expert level analysis to underserved areas, reducing costs of medical imaging interpretation, enabling faster screening programs, and supporting less experienced healthcare providers and communities.